a different route through the education system. He started high school in Colorado, and from Colorado he went to MIT, and there he had the good fortune to have Dan Kleppner as a freshman advisor, so he started very early doing real research, and he has written somewhere that he tried to avoid courses as much as he could. But finally he ended up with his undergraduate education, and then he went to Stanford for his PhD. And by the end of, well, just before he finished his PhD, he started to get interested in trying out the then new electroweak theory and trying to work on the parity violation. And for that reason he went to Michigan, where they worked on a hydrogen experiment. And one early achievement of Carl was to find a way to compare merits of different experiments, and he found that it would be a better bet to work on cesium. So he started to work on that, and he left the hydrogen experiment. And by the time that this had matured and got some attention, he got an offer from Colorado Boulder, and there he went. And in 1 year, he got married and had this experiment ready. And that was in 1984, was it? Yes. And then that experiment and the development of that led into those things that gave him eventually the Nobel Prize in 2001 for Bose-Einstein condensation. Now, I also want to mention that that was in 2001, and a year or two later he got the US Award for Best Teachers at the university level. And now he is working more or less full-time on education. So please, Carl, the stage is yours.
Thank you. Okay, it's a pleasure to be here. Is this working? Yes. Oh, okay. Good.
No, I think
No?
It's working.
Well,
Everywhere.
oh well. Can you hear me if I just talk like this? Fine.
Louder.
Louder. Yeah, the microphone isn't working, so.
Turn it on.
Try not.
Yeah.
Okay. I was told to put it in the other position to make it work. Okay, now it's probably too loud. But, yeah, so I'm going to talk to you about really using the tools of physics to actually be more effective in teaching physics. But before I do, I want to emphasize that the fact I have a Nobel Prize doesn't mean I know anything about teaching science. I mean, that's really a very different subject. But the reason you should pay attention to this and believe that I do know something about teaching science, or at least what I'm going to say in this talk, is that it's all backed up by lots of data. This is research in science education, particularly in research on the learning of physics that's come out of a lot of different groups, research groups all over the world. But I actually, some of it comes from my own science education research group that I've now had for about 10 years, exploring these topics. So what I'm going to cover today is first just a quick introduction about the importance of science education in the modern world, and then look at some of the research on the effectiveness of traditional teaching approaches and how some ways to improve them, and then finish up with really talking about some technology that can really help improve education if used right. Now, I think it's important for everyone really to realize how science education is actually become much more important than it's been historically. And the reason for that is two big changes in society. First, mankind is really faced with some enormous global problems that are basically technical in nature. And so if we're going to have populations that can make wise decisions on some really critical issues like global warming and genetic modification and so on, they have to understand science a lot better than they do now. And then, of course, the second one's the economy. The modern economy is so based on science and technology that it needs a lot more scientists and engineers to make it function, and pretty much independent of your occupation in the modern economy, you'll be more successful if you understand some science and the sort of complex problem solving that science involves. And so because of these changes, what it means is that we science teachers can't afford to just worry about training the next generation of scientists, which has been our historic purpose. We really have to think about how to make science education effective and relevant for a large fraction of the entire population. Now, the good news is that all the research indicates that if we do this job well, we'll do this job even better. And I can say more about that at the end if you're curious. Okay, so I say we have to make science education effective. What does that really mean? Well, the way I would define it, and the standard I'm going to use for evaluation, is really it's transforming how students think. So they come into our classrooms like this, and we want to have them go out transformed. See? Now, admittedly, most of the time, there won't be quite such a transformation to turn into science, literally turn into scientists overnight like this. But basically, I think the goal of a good goal of science education at each level is to have the students come through the class thinking about science and using science more like a scientist. And that's really the criteria which I'm going to use in all the kind of research studies I'm going to show you on how well we're doing at that. So, accomplishing this for large fraction of the population is an unprecedented challenge, and it's, not obvious that it's even possible. But the hypothesis that I'm putting forward, and lots of other people, are that we can achieve this much more effective education, but only if we think about teaching in a different way. And we start approaching the teaching of science just like we do science, and using some of the basic practices that have been so important and effective in physics. And the ones I have listed here are all things that are really at the heart of any experimental physics program, and a large part of why physics has progressed so well. And I'm going to argue that we can apply those just as well to education. By this, for example, practices that are based on good, rigorous, objective data, not, as is so much the case in education, of tradition and anecdote and even superstition sometimes. Second, being guided by, the results of principles that come out of fundamental research, in this case, fundamental research on how the brain works and how it learns. Disseminating the results in a scholarly way and copying what works. We all know that in science, if you move into a new area, you go read about the state of the art, and it's all written down in papers, and you start out by copying that and you improve from that. That's not at all the way we work in education, but there's no reason it can't be. And then finally, just fully utilizing modern technology, taking advantages of these. Like I say, we all know that these are critical to success of science, and I'm going to show you how these can be equally valuable in improving the effectiveness and efficiency of education. And so really the rest of my talk is sort of laying out the case to justify that. And so I'm going to do that by looking by looking at what research tells us on the effectiveness of traditional science teaching. But before I do that, I want to sort of lay out the context of how I came to start thinking about this in a different way. And it goes back to when I was first called upon to teach physics many decades ago. You know, I think it was introductory electricity. And I used the basic approach. I think it's basic kind of human nature to teaching anything. Your first reaction is I go and think really hard about the subject and get it all figured out really clearly in my own mind, and so that then I could go and explain it to these beginning students, and so they'd understand it with the same way I did and the same clarity I had. Well, that was the idea, but unfortunately, well, or fortunately, I've always been a really hardcore experimentalist, and I would actually measure how well this was working. And it was clear that for the vast majority of my students, my brilliantly clear explanations, they left them just completely baffled. It really wasn't working at all. And I did some actual little tests, even way back then, on students from other professors' classes, and it was clear it wasn't all that great for them either. So for a long time, this was just kind of a frustrating puzzle to me, and it really wasn't clear to me you could teach physics effectively to a large fraction of the students. But what actually led me to make understand this a lot better and think about it better was working with graduate students. I had a big atomic physics program for many years, and so I spent a lot of time paying attention to graduate students and how they developed, because their success was my success. And over the years, and with enough students, I came to see a very consistent pattern emerging. And that is that these students, they would come into my lab to work, for me and their PhDs, and they had been, by definition, they wouldn't be trying to get into my lab, they hadn't had 17 years of tremendous success in physics classwork. And yet, when faced with real physics research problems, they just had no idea what to do. And, well, but the thing was always really surprising to me is just a few years later, working in the research lab, they were transformed into physicists. They were my equal colleagues. And, if I'd seen this happen just a few times, I think, well, this is just a kind of peculiar thing about this individual. But as I say, after going about 15 PhD students and seeing very much the same thing, I decided, there's a real pattern here. There must be some explanation for this strange behavior. And that it didn't just, didn't make any sense to me, but there must be something basic going on here. Now, one hypothesis that I had, and many others who've seen this same effect have had, is that, well, maybe it's just that the human brain has to go through sort of a 17-year caterpillar stage here before it can suddenly be transformed, into a physicist butterfly. And that's not a crazy hypothesis, but I wasn't satisfied by this, and so I really tackled this like I would a physics problem, of really going out, reading the literature, looking at research on how people learn, particularly how they learn science, and to make better sense of this. And from that, I really came to the conclusion that, in fact, well, this wasn't the explanation, but this made perfect sense, in fact. And in that understanding also gave clear ideas of how we can improve the regular classroom teaching that we do at universities. And so I'm going to give you some examples of some of the typical data that led me to that conclusion. And so this is data first on the effectiveness of traditional science teaching. And by traditional science teaching, what I mean is I think it's probably vast majority of science classes are done like this here as all over the world, and that is that the primary contact between the instructor and the student is the instructor is lecturing like this to a largely passive group of students, some of them already asleep. And then they, the students go home and they do problems in the back of their textbook, and they have similar kinds of exams. And so there's now a growing body of research carried out by scientists on the effectiveness of this practices. And I've picked 3 intentionally very different aspects of this learning to look at. One is just the retention of information from lectures. 2 is conceptual developing an understanding of concepts. And the 3rd is really much more general beliefs about what physics is and how it's learned. And then I'll say a little bit of work that comes out of cognitive science, just to kind of some underpinnings to understand those results. I should say that most of the data here comes from research looking at introductory university physics courses, but we have a growing body of literature now that's covering both higher and lower level courses and other disciplines, and they're all giving very consistent results with the sort of things I'll tell you about today. Okay, so retention of information. I mean, you think about a lecture, it's the idea is transferring information from one person to many, and it's actually pretty easy to test how well that works. And there's been lots of kind of formal studies where I'm going to give you 2 that are just quick and easy things anybody could duplicate. The first comes from Joe Reddish. Now, Joe was he's a physics professor at the University of Maryland, was considered one of their outstanding lecturers. But he was a little like me, and he started worrying about, well, how much were students really learning, even though he was getting these evaluations saying he was a great lecturer. And so he actually hired graduate students to capture at the end of class, when students are filing out of the lecture theater, to just capture them and at random and do interviews and ask them, what was that lecture you just heard about? And what he found out consistently was the students were able to explain only just the vaguest of generalities of what they just heard from this person who was supposed to be one of the best lecturers at the university. And another little study that I did with Kathy Perkins, we would take some non-obvious but important idea that we introduced in class, and usually with some sort of illustration, and then using some technology I'll talk about later, using 15 minutes later, we would just test the students on whether they remembered this thing that they'd been told. And we found out that typically about 10% of the students would actually remember this 15 minutes later. Now, as I say, there's lots of other much more extensive structured studies, but they all give this same basic idea that there's a tiny fraction of the information that's being transmitted in a lecture is actually being absorbed and retained. Now, you ought to be worrying about this, particularly if you're a teacher, because, we have thousands of science lectures going on every day. Should worry, can this possibly be generic, that such a small amount of information is being retained from these? And what I would argue is that, in fact, if you look at cognitive science, there's very good reasons to believe that, in fact, it almost certainly is generic. And that it gets at something called cognitive load, which is really one of the best empirically established results from cognitive science and is widely ignored in teaching. And it's really well represented by this cartoon. And it's basically, the idea is that the short-term working memory, the part of the brain that remembers and processes information on sort of short time exposures, like an hour-long class, that short-term working memory has extremely limited capacity. That's in contrast to the long-term memory, which has a very large capacity. And so cognitive scientists have measured this in various different ways in their labs, and they'll tell you that the typical human brain can hold and remember about a maximum of about 7 items in this short-term memory, can process a maximum of about 4 ideas at once. Now, exactly what this means when you translate ideas and items from their lab into the science classroom is kind of fuzzy, but the one thing that's really clear is that this is just a tiny capacity compared to the amount of information and processing that a student's really called upon to do in a typical science class. And so, knowing these fundamental limitations of the brain, it really would be quite astonishing to see that students were taking away anything more than a very small fraction of the information that they were being presented for the first time in a lecture. Now, in that spirit, I have to say, since I know all of you have human brains, and I'm probably going to go over your capacity, but I will make copies of my slides available as a pseudo long-term memory. Okay, well, that's just retention of information from lecture. Now, I think most of us would argue that's not really the most important part of learning. There's much deeper things in learning physics, and one of those would be really understanding of basic physics concepts. And there's been a lot of research looking at how well students actually master these concepts from introductory physics courses. And in the process of these studies, people have developed some very good tests for probing that learning of concepts. One of these, the most oldest and most widely used, is something called the Force Concepts Inventory. I'm just curious, how many people here have actually heard of this before? Okay, so there are a few of you. So what this is this is a very carefully developed test that takes the basic concepts of force and motion that are covered in basically every first semester physics course given at any university and college around the world, practically. And it probes students' understanding of these concepts by having them asking questions in which they have to apply them to some sort of simple, usually real-world example, like when a car runs into a truck, or in this one, where there's a ring sitting on a tabletop and a ball rolling inside it. Which direction does the ball go when it comes flying out of the ring? And so this test is actually now given in hundreds of courses, particularly in North America, every year. And the way it's used is one first has the students go through this test and do the best they can at the start of the term, and you look at which questions the students get wrong, and then you have them take the same test at the end of the term after successfully completing the course, and you see what fraction of these courses did they get wrong at the beginning that they got right at the end, and that sort of tells you their percent learning gain. Of course, you'd like to see it as 100%. But it turns out if you do that and you look at the average fraction gained by all the students in the class, you get a very consistent result. And it's shown right here. This is a compilation from 16 different courses, the average fraction learned by the students. And you can see it's always less than 30% of the concepts that they didn't know at the beginning of the class. And this is, now I should say, this is for courses that are taught using a traditional lecture approach. And I know lots of other unpublished data that piles up here in the 10 to 20% range. Now, the thing that's most remarkable about this is that this holds true independent of the quality of the lecture, you know, whether they're considered to be really good or really terrible, whether it's big classes or small classes, or whether it's Harvard University or your local two-year college, this basically, those all are in this range. And so it really says that this traditional lecture approach is simply not effective for having students develop a mastery of basic physics concepts. And this is actually really probably one of the most important results in science education that's been achieved, and it's really having an important impact on changing science instruction, as these quantitative results are just so compelling to many instructors. Now, the other thing that's important, though, is using this same instrument to measure the learning of concepts, using new approaches to teaching driven by this research. People are now consistently getting up in this range of factors of 2 or 3 improvement in the learning gain of these students. And I'll talk a little about in a minute what goes into that. Okay, but now I'm going to switch to a totally different kind of learning, and it doesn't really involve content at all. It's really aspects about just beliefs about physics and what it means to learn physics and how physics solves problems. And it turns out if you interview a whole lot of people, you find their beliefs lie on a scale which we call novice to expert. And I'll just show you what I mean by these beliefs by defining what a novice and expert are. So novices in physics see the content of physics as just a whole bunch of isolated little pieces of information, and the way you learn physics is just to memorize all these little pieces of information. This information is handed down by some authority and completely disconnected with the world outside the classroom. And physics problem solving is about just matching memorized recipes and formulas to the pattern of what the problem you're given. Okay, so that's how novices see things. Experts, like all of you as practicing physicists, well, maybe not him, but all the rest of them, they see the content of physics, of course, as this, coherent structure of the very general concepts. These concepts describe nature and are established by experiment. And, physics problem solving is about using these systematic concept-based strategies which are widely applicable, including into new situations we haven't worked with before, and of course, therefore, much more useful than this approach. So once you realize people's beliefs lie on this scale, you can, with a little work, and this is something my own research group is one of the leaders in, you can develop a survey instrument that can characterize people's beliefs. And so you can now use this to see, okay, how effective is our teaching? So you can measure all the students and their beliefs and look at sort of their average belief of the students at the start of the class here, and they're presumably going to be somewhere a bit over on the novice side in an introductory course. And then you want to measure, okay, so how much more expert-like are their beliefs about physics as a result of successfully completing a physics course? Well, that's what we'd like to measure. What we in fact do measure this is now, between our own group and all the other people using this instrument, been done on a lot of different physics courses. And the University of Maryland group does similar kinds of studies. We find that, except for a few special experimental courses, the normal introductory physics course leaves the students more novice-like in their beliefs as a result of completing this course than they were before they ever had. Okay. Now, this is actually, if you think about sort of general science literacy, this is an extremely disturbing result because, it means that we're sending people out that from our education system and our courses actually seeing science much more like this than they do like this. And I have to say, one of the most worrisome results we have is that of all the different populations of students we've looked at, by far the most novice-like in their beliefs about science are actually the students who are about to become elementary school teachers. So, anyway, we've studied this a lot. I don't have time to go into the details, but we've seen that these beliefs about science correlate with how well the students actually learn the content of physics. We see that these basic beliefs, they have nothing to do with ability or knowledge of content. I want to emphasize that. They're much more kind of like religious beliefs. You're just view general beliefs about science. They're a very powerful filter as to who goes into physics and whether they stay in physics. And so if you're concerned, and I can show you some of the data later if people are interested, but the point I'll just make here is that if you're concerned about trying to get more students going into physics, probably the single most important thing to do is to worry about their general beliefs about the subject here. Now, we've been looking a lot at teaching practices, and like I showed you, the normal teaching practices cause a decline in these beliefs. It also causes students to be less interested in the subject, because those things are closely related. But it turns out we haven't had time to do a lot of research on this, but some rather simple things can actually make substantial differences. And simply recognizing and explicitly addressing beliefs gives quite significant measurable improvements. And by how do we do this addressing beliefs, it turns out just making sure that as each topic is presented, that you're wanting students to learn, making sure you talk quite explicitly about, why this is worth learning, how does this, physics topic, connect to the real world and understanding it, and how does it connect to things the students already know. And doing nothing more than that, we see, makes a significant improvement. Okay, so I sort of talked about these different classroom results of students becoming less like experts in their thinking, even though they're being taught by experts and not learning concepts. And it's useful to recognize that this can be understood at a more fundamental level from looking at work in cognitive science, and particularly the work on expert competence and how it's developed. And so cognitive scientists have studied what makes an expert, and they find there's certain characteristics that go across a whole range of different areas. And one of these is experts in their, know a whole bunch about their subject. That's sort of obvious. But there's a couple of other important things. Experts have unique mental organizational structures that basically allow them to effectively retrieve and apply all this knowledge they have. And these are specific to the discipline. And so what I would argue is when we think about physics concepts, those are really the way we organize information about physics to use it effectively. And then experts also have an ability to monitor their own thinking, to test, is this a sensible way to be trying to solve this problem? Do I really understand this? How can I check this? Turns out experts can do that in their subject. Other people can't. And so when you recognize this, you realize that there's really kind of an implicit assumption in the traditional science teaching. And that is that if we just get the students to have the factual knowledge, these other aspects of expert-like thinking just come along for free. But in fact, that's not what the classroom studies are showing us, as I just pointed out. It's also not what the cognitive science studies show us. The cognitive science indicates that these aspects are really new ways of thinking. And they only get developed through an extended, focused mental effort that sort of constructs in a student's ability to think that way. And that development is always based on their prior thinking and understanding, and so if it's not built on, if that foundation isn't there to start with, you won't develop them effectively. And these are actually almost biological in origin, in that everything we think about as kind of expert understanding and competence is all built in the long-term memory, and these are fundamental characteristics to developing long-term memory. So there's just kind of no way around it. It's fundamental to everybody, and that's why it makes sense that it turns out to be so generic across disciplines. Okay, so when you have this view of understanding of how people learn and so on, now this puzzle that I was talking about at the beginning makes a lot of sense. Because these students were doing great in these classes, but those classes, as I showed you, aren't effective at developing expert-like thinking. But if you look at what does develop expert-like thinking, I can sort of summarize a lot of work in a principle here, that people really learn by creating their own understanding. And therefore, effective teaching is really just the facilitation of their development by getting them engaged deeply in thinking about the subject, and then monitoring and guiding that thinking to become more expert-like. And when you put it in those terms, and then you think about what happens in an atomic physics research lab like mine, this is exactly what the students are doing all day long. If you listen to them, 7 days a week, 18 hours a day, continually, and that's why it's such an effective way for them to become physics experts. It's not the magic atmosphere of the lab, it's the cognitive processes that they're engaged in. And once you realize that, then it tells you how we can do a much better job of improving classroom instruction, is to get those same kind of cognitive processes in the regular classes. Okay, so, does this work? The answer, I'll just show you some data. I don't really have time to go into the details of how these things can be implemented, but lots of people are working on trying to do this and doing research. And here's some, just since I emphasize we need to approach this like science with data, we've seen dramatic improvements in retention, this learning of concepts I already mentioned, getting factors of 2 and 3 gain, and I already mentioned we with just starting to learn, making the simplest changes, we're already able to eliminate this big drop in attitudes and making it at least a little improvement. Okay, so like I said, I don't really have time to talk about details of implementation, but I want to just give you a basic idea of what's involved in this. What you first have to do is make sure you get the students really engaged in guiding their thinking. It means you have to know where they're starting from and build from that. There's just no way around that to have effective learning. Secondly, obviously you have to get them actively processing ideas, and realistically that's has to happen in the classroom, because that's the primary opportunity for instructor-student interaction. And so you need to think about ways you can get them in the classroom processing ideas, and then you find out as an instructor how to effectively guide their thinking. But that's a start. It's not enough. And you also have to keep them, then spend much more time than they've ever have available in the classroom, continuing this development. And so that means, having homework problems that are authentic, have them really deeply engaged in exploring the physics ideas, and then having ways they can get feedback on how they do that homework. And the reason I emphasize this is so important is because no matter how wonderful a job you do in the classroom, it's just not enough time. I talked about developing long-term memory, and to do that, I mean, basically the brain has to build these little proteins and put them together in certain structures, and there's fundamental time limitations on that. And so if there's just no substitute for having to spend a large amount of time and focused effort in order to do that long-term memory development. So you have to have that as part of the learning. Okay, so I'm going to talk about how does one do this in the classroom. Well, I think a good instructor with 1 or 2 students could probably do this without much trouble. But, I usually teach in student classes of 50 to 200. And then in a classroom like this, then it's much more challenging to figure out how to do this. But this is where technology, actually, we've seen, can be a major help. And so I'm going to talk quickly about a couple of different technologies that my group has been exploring to do this. Just as some examples. So the first one is using clickers or personal response systems, which I guess they're not used around here, right? People aren't familiar with this? Okay. So what these things are is a clicker is something that's about a little bigger than a laser pointer. Each student has one. It's coded to them. It's actually kind of a miniature television remote with buttons on it. And so basically the way these are used is the instructor can talk for a few minutes and then stop class and pose to the class a question like this. And then the students think about it, pick what the answer is, push the button that they think is right. The computer then records who they were, who they are, and what answer they picked. And then usually after all the answers are in, the instructor will then display a histogram as to what the responses were to the class. So it's a way of finding out, basically, checking understanding of every single student in the class very quickly, immediately. Now, this technology isn't automatically helpful. It just provides a few basic features, and I've seen many examples where they're not really being used very effectively. But they really, if they're used right, they really can completely transform a classroom. And so I'll just give you some quick guidelines as to what my sort of extended science education initiatives have looked a lot at the effective use of these things, as have many other people. And some of the key things are to make these really challenging concept questions that the students really have to think about, and in addition, to have them talk to each other. So I'll have each little 3 people sitting next to each other, kind of a consensus group, might have a minute or 2 to argue about, figure out what they think the answer is and the reasons behind them before they submit the answers. And then there has to be appropriate follow-up, and so that if the students miss it, some fraction of students miss it, you really have to bring out the reasons that they're thinking that were wrong, and so you can effectively talk about what's the aspects of the right ways of thinking and wrong ways of thinking about it. And this process gets the students much more deeply engaged in thinking about the subject, but that also provides much more effective feedback for guiding their thinking. So they just learn much more. And this is the kind of thing that gives those dramatic improvements in the conceptual gains as measured by things like the force concepts inventory. Okay, I'll just finish with one other technology that my group is, I have a big group developing here. This is called these are interactive simulations, and this is this project. You can get to these. These things are available for free. You can run them online. You can download them to your own computer. And we've got them now for quite a range of physics topics, ranging from rather simple things, the balloon and sweater that I'll show you, up to a whole bunch of actually quantum mechanics simulations. This is an example of quite an accurate model of a laser. So let me just show you a few examples of some of these. And by the way, if anybody wants to translate them all in Swedish, we got it, so it's really easy to do that now. So, okay, so on this one, for example, you've got the balloon here. You just grab it with your mouse. You can rub it on a sweater and pick up electric charges. And now there's a force that's, appropriately proportional to how many imbalance of charges. You take it over to the wall, it polarizes the wall, and you can see why it sticks to that, as long as it's really close. Otherwise, it gets pulled back to the sweater. So that's a really simple one. Getting a little more sophisticated is this moving man. And I don't know how many of you have been called upon to teach students about graphs of motion, but it's actually a very challenging idea for students to learn. And this actually helps them learn much more effectively. This one, you just grab this little guy, and you can drag him around, and it plots velocity and position and acceleration. Or you can go then and play back over these graphs or other graphs that you might have the students create on their own, and it just shows you, then displays what that motion corresponds to. And like I say, we've got pretty good data showing that this is just makes it dramatically easier for students to understand what graphs of motion are all about. Our best seller here, now I'm going to get to one that's a little more complicated. This is the circuit construction kit, and you can basically build any circuit you want. There's an AC version of this as well. It doesn't involve transistors, and you can build, and so I built most of this ahead of time. I've got to hook up one last wire, then I close the switch, and the electrons move. Light bulb lights up. I can increase the voltage, and the electrons move faster. And the light bulb gets brighter. I've got voltmeters and all these things. You can go and measure voltages, different places around the circuit here. And so, you can see this is a great way for students to play around and learn about electricity. I've got to show you one. I'm going to take extra time to... I only get to show this in physics audiences, so I have to show this. This is one of my favorite features here. If you watch carefully on the... I'll just kill off the circuit here for a minute. Okay, watch carefully on the resistor. As I change the resistance, you can see the color code also changes. Can't resist showing. Anyway, so this is a completely new kind of educational media. We have a lot of data showing its use is highly effective. But in the study and development of these, it brings out basic characteristics that show up in science education or education research in all different ways. And so I'll just leave you with a few final thoughts. It's first that students, don't know something. They really do think and perceive differently from experts. It's not just that they're uninformed. Their brains are quite literally different. And we see this very much in how they perceive what's happening on the computer screen and how that changes as they become more expert-like. It's also, we see that learning is something that it's really created or discovered. That if you've got a fancy animation, students pay a lot of attention to it, but they don't learn anything. It's really when they're in there asking themselves questions and manipulating things and seeing the responses, that's when really their understanding develops. And so it really is this idea that they develop their own understanding. And we can simply, the beauty of simulations is we can build the characteristics in need to make this happen. So I'll skip what I'm doing at UBC, which is just trying to get this into all the classrooms, and just end up with the conclusion that I think, this scientific approach to science education really there's opportunities for really dramatic improvements over what we've traditionally used. If you want to learn more about this, here's a bunch of good references, starting from a long book that's well written to a short article that's poorly written. And this gives our survey about physics beliefs and the research we've done on it, and this gives all those simulations and also research papers on we've learned about learning those. So, thank you. So I'm happy to answer questions or hear arguments for as long as people want to stay. So I think if you just call them out, I can.
Could you just give an example of what you meant with cognitive processes in the research lab? A concrete example.
Yeah. So what they'll have people. You mean in terms of this cognitive load aspect of?
Well, you said that they develop so well in the lab. Your grad students.
Oh, I'm sorry. Yes. So what I mean by there is that, I posed an authentic problem to them. This spectrum is coming out of this atom. Why is that happening? Okay. And so they're sitting there, they're trying to understand all the physics going on, and then regularly I'm coming in and saying, okay, what do you think's going on? They're explaining it to me, and I'm telling, well, I think that part makes sense, but doesn't, are you really worrying about this properly? And so that's what I mean about them, being deeply engaged in trying to figure things out, solve problems, and then having someone there probing that thinking and giving them feedback on what's right and what's wrong about it.
Could you comment on why Finnish students, for example, do so much better than U.S. students in international assessments?
So the answer is no. I can't comment. Well, I hear speculations that the teaching profession in Finland is considered it's a much more elite profession. The people going into it are much more qualified. I know for a fact that people who go into teaching science in the U.S. are basically the dregs of science students. I mean, we have data showing that the teachers, they mean well, but their understanding of science, their beliefs about what science is and so on is dismal. And so I certainly can believe that's the explanation, but I personally don't have any data that I've seen to prove that.
Can you comment on whether there is similar work done in mathematics and whether it's similarities or differences between physics and mathematics?
So, yeah, there's this sort of discipline-based education research going on in a variety of fields. There's significantly more done in physics than in other areas. In mathematics, there's quite a bit of good research done and published on lower level learning of mathematics, like algebra. You can go read papers that are really, have some really good research in them. There's a lot less done on mathematics at higher levels, like calculus, and it's a deficiency. There is some, I'd say, all the kinds of basic conclusions about what's important for learning and helps learning and hinders learning seem to be quite consistent with what we see in physics, what we see in chemistry, and so on. But it's a rather relatively sparse literature and small community right now once you get above those lower grade levels.
Cecilia?
I remember when I was learning mechanics, I hated it because it was about cannons and guns and, you associated with killing.
Yeah.
And when you find out about nano and things like that, it became by far more interesting.
Right.
Do you know if physics should be taught to girls and boys in a different way in order to be efficient? Or
So what I would say is, if you, motivation, I talked about beliefs, okay? And there's sort of your beliefs about the subject is strongly coupled to your motivation to learn it. And so we do know that people, different people have different backgrounds and beliefs or different experiences that shape how they respond to different things, whether it's boys and girls, whether it's, whether it's your cultural origins and so on or not. We do know those make a big difference. And so when I said that you have to appropriately connect with your students' background and initial perceptions if you're going to help them learn effectively, that's basically just repeating or, exactly echoing what you're saying. Is that, there's things that boys respond to in general differently than girls respond to. But even at the low, you need to even get somewhat more fine-grained than that. Students who come from, in the middle of a big city and are poor, if you want to have them motivated, have things make sense and see there's a reason to learn it, you need to pick different examples than if they have very different backgrounds.
Do the cognitive studies say anything about the length of the teaching model, sort of optimal length, in terms of the amount of information that's being transferred for?
So it gets really quite complicated in terms of those time scales and how things are getting coupled. I'll give you one very simplified statement, okay? This is, like I say, this is oversimplified, but that you better have gone back and seriously processed something a second time within 20 minutes or you'll pretty much lose it, but you've got to have that kind of repetition within that time scale. And in terms of, so think of that as kind of a time constant. It's not quite as simple as that. One thing I'll emphasize on that that's really important is that the more you can connect things up and call on long-term memory, the less you fill up this really limited capacity short-term working memory. And so things like analogies, that's why they work, is that basically they're coupling this new material to stuff that the person's already familiar with in their long-term memory, and therefore, there's just a little bit extra that they have to adapt, and they don't fill up things nearly so much.
At the beginning, you showed us view graph with how much one can actually remember from one lecture. But do you have any suggestion what to do when you have to teach according to some program and the student is supposed to remember much more than your lectures allow for?
Right. Yeah. So the first thing you've got to ask yourself is, do you believe that students can't learn something if you don't cover it in the lecture? And the second question you've got to ask yourself is, do they learn it if you do cover it in a lecture? Now, I know the answer to both those questions, all right? And so what you need to be thinking about is, gee, if you're just transferring information that you want them to remember, there's much more effective ways to do that than you telling them. So you want to use that precious class time period to do really important, useful things that you uniquely can do, which is guide their cognitive development, guide their thinking, and then have them go, all this stuff they got to memorize, and there certainly is some of that, but they'll memorize that better at their own pace over an extended time outside of class, reading a book or reading notes you want to give them. So it's just a question of that's the optimal use of time and resources.
There has been a shift from blackboard teaching to PowerPoint teaching.
Right.
Do you first of all think that this is a shift in the wrong direction, or do you think one should actually go orthogonal to that direction?
I think that it's there's no good answer to that, because I look at these as just different technologies. If you take a computer and you're using it as a doorstop, that's probably not a very good doorstop and not a very good use of a computer. And so it's all, with any technology, you've got to ask yourself, how can this be used in the most optimum effective way? So you can use blackboards badly, or you can use them well. You can use PowerPoint badly. It's probably a little easier to use PowerPoint badly. Lots of people do, I'll just say. But at the same time, it does have capabilities that a Blackboard doesn't have, and if you take advantage of those, it can actually be superior. But, there's no one better or worse. It's simply how they're being used.
For obvious reasons, of course, you're limiting research to examples from physics, and this is what's interesting for all of us here. But do you see any reason why anything you've said should not apply to any subject?
So it applies. So all of the things I've said about the basic cognitive science, limiting on short-term working memory, developing expert competence, that's absolutely general. I'll make that statement. The other things, I'm confident they apply to science. There's enough research data to prove that. I'm now involved in working with enough departments to say there are certain unique learning challenges that each discipline has, but the generic ideas clearly quite generally apply. As you get farther out from science, I'm a little more reluctant to make claims as to how general, just because I can give you an opinion. An opinion is most of them apply. I'm not sure all of them, particularly as you get more artistic things. But, my central thesis is you've got to treat this as science and go by what the research tells you. And outside of science and engineering, I don't know of much research that you could really point to. But, the basic cognitive science stuff strongly suggests that most of them would apply. It's a polite group. Usually there are at least a few people who want to object to my sweeping statement.
So, there are no hands, so let's thank the speaker again.